Right. Right. Thank you. Thank you very much. And also thanks very much to the EMI Network Foundation, University of Turku, University of Helsinki. This is like our threesome cooperation. So it's been really a pleasure and very happy about this meeting. Anyway, so here it goes. I start by just with the question: is the brain analogous to a quantum measuring apparatus? If you worry about analogies, then I want to show I'm in good company. We got Aristotle, who said that the greatest thing by far is to have a command for metaphor. This alone cannot be imported by another. It is the mark of genius, for to make good metaphors implies an eye for resemblances. This is in the Poetics. Also Niels Bohr, much later, Atomic Physics and the Description of Nature, when said, although we can be concerned only with analogies, yet in the facts which are revealed to us by the quantum theory, we have acquired a means of elucidating general philosophical problems. So this is kind of also my general approach of what you might call quantum philosophy or scientific metaphysics. That if you like, bitten by the quantum bug at some stage, and then you go with it for the rest of your life, even in philosophy. Anyway, so the question here I want to talk about or get started is this issue about the classical versus quantum world. It has been already discussed to some extent. And we could say this is one of the key questions in quantum mechanics: what is the relation between the classical world and the quantum world? And for these questions, the interpretations of quantum mechanics differ. I'm sorry this is a bit small, but anyway, the usual Copenhagen interpretation with Bohr, the situation that actually, people don't always realize, but quantum theory actually presupposes the classical level. Because remember, it's all in terms of observation, and to make observations you need a classical measuring apparatus. And you see, in this approach, as you move from quantum to classical level, some features appear, namely particles, because you don't have particles in the Copenhagen interpretation, and other disappear, like interference will disappear. Actually, Paul Feyerabend makes this point nicely in one of his articles. Now then, of course, we have the spontaneous collapse interpretations like Girardi et al., Pearl, also Penrose, and Diossi, where, to put it simply, classical objects emerge through a collapse of the wave function. We got the many worlds, Everett, etc., where the world at the macroscopic level branches in each quantum measurement. So it's not necessarily that an entire universe is created, but you can also see a kind of more sober version of the Everett, which presumably was Everett's own view. And then there's the de Broglie-Bohm, where we get classical behavior whenever the quantum potential has a negligible effect. And this is, of course, what Basil was talking about, the quantum potential. So what I'm going to be focusing is on this Bowman-Hiley's ontological interpretation of quantum mechanics. I call it BH. And here, of course, a quantum object, such as an electron, is a particle accompanied by a new type of field, described by the wave function psi, which satisfies the Schrödinger equation. And that's from the field we get the quantum potential. Of course, Basil does it differently these days, but still, this is more like the older version.
I think it's easier to stick to the older version.
Right, over here, yeah. And also one thing you notice is that the quantum potential depends only on the form of the quantum field. It's thus informing rather than pushing and pulling the particle, which is like analogous to a radar wave guiding a ship. And this is actually a scholastic notion of information as informare. And it's kind of connected also to Giulio Tononi's notion of information as the difference that makes a difference, going back also to Bateson. Anyway, some other features is that the quantum potential between particles need not become weak as their distance increases. So we got non-locality and context dependence, again explained by the quantum potential, and the quantum potential for a many-body system, for example in superconductivity. It constitutes this common pool of information that guides the particles in a holistic way. This is again something that Basil showed us mathematically, just kind of revising this. This, you might say, is analogous to ballet dance, so we have quite a kind of quantum ballet, where interactions between particles may not be describable by a single pre-assigned function, but there's this common pool of information. This is something actually Bohm himself felt is the most radical new feature of quantum mechanics. And finally, in certain, but this will be like one of the key points in my talk, is that in certain situations, the quantum potential has a negligible effect, and we get classical behavior. And I'll be repeating this point, so I hope you won't get bored. Anyway, this is just a slide from Basel, which he showed. You know, in the famous two-slit experiment, the particles are coming from these holes toward you. If it was classical mechanics, they would just typically go in straight lines, right? Not like this with straight lines. But now we have this quantum potential, which you calculate from here. It's a second spatial derivative of the r, which is the amplitude. It only depends on the form, not on the size. But anyway, so that's the thing you get here. Potentials you can think a bit as mountains. So depending on the energy of the incoming electron, most of them, they don't want to go up here. They don't have the energy. They like to go here where, you know, it's nice and you don't have to work so much. And you can see how these two pictures go together. So nobody goes to this region where the thing is high, but they like to go into these things. And now we actually get an explanation of the bunching of the trajectory. So this is, of course, one of the selling points of the Bohm theory. We can actually give an explanation of the two-slit experiment, which was supposed to be impossible. Of course, one should, like Basel emphasized, these are hypothetical. Because of the uncertainty principle, we cannot actually observe an individual thingy. We cannot observe whether anybody is there taking a trajectory, but at least we have a hypothesis. And with the measurements of weak values, the average trajectories look very much like this one. So, you know, there may be something there. And the other point people are making, that the trajectories are actually, they are implicit in the Schrödinger equation. They are part of quantum mechanics if you want to have them. You don't need them, but they're there. Okay, but enough of that. Okay, so let's ask this question. How does the ontological interpretation view the relation between quantum and classical world? And this is something that I'm using. This is partly a tutorial on undivided universe, because I just want to draw attention to some of these ideas. Now, the way Bohm liked to put it is to say that there's a single world, what he called an overall quantum world. There should be L world. And in this world, you have particles and fields, as in classical physics. So that's part of the ontology. But it's not classical physics, because these are profoundly affected by the wave function through the quantum potential and the guidance condition. And so we get these features like form dependence, contextuality, non-locality, and organic wholeness. Therefore, this is not classical. Well, you know, people sometimes want to say, well, you know, Bohm is just going back to the classical, but it's not like that. Now, the thing is, of course, that this quantum behavior is very different from what is to be expected classically. For example, the trajectories that we just saw. But again, the point, when the quantum potential is negligible, a classical subworld emerges within the overall quantum world. So this is how, remember, this is an ontological interpretation, and we can expect from it, like a world view. And this is how we have to think about it. There's this overall quantum world, and within it, there's this classical sub-world. Oh, sorry, you can do the point here. Now, Bohm, of course, liked play with words, etymologies, and being perhaps a bit poetic. Of course, some people don't like, but anyway, one of the words he used a lot is the word subtle. And he would say that the quantum world is subtle. Why? Well, you have this kind of all the weird quantum behavior, things like particle interference and non-locality. And this is just, of course, just giving you an intuition of something. Whereas in contrast, the classical world, he would say, is manifest, something we can manipulate. This, of course, connects a bit with Tononi's talk, because for him, this is, of course, important that you can manipulate. Now, one thing to realize here is the quantum world is actually very elusive. Unlike the classical world, it cannot be manipulated. If we try to hold it in a measurement, we get these unpredictable and uncontrollable changes. That's the uncertainty principle. it's holistic in the sense that each element participates irreducibly in all the others. You remember Wheeler, the participatory universe. You have it here also in a certain way. And again, it's very difficult to grasp with our instruments, like, it's not manifest in the same way. However, Bowman highly would emphasize it's real and constitutes a more basic reality than does the classical world. So this is again something where we have to learn to think in a new way. The foundations of the world could be much more elusive than these things over here, which are, and of course, like Tononi would say, that maybe these things are the ones that have the existence. Of course, once you have a certain kind of, these connections. But here it's not like that. Here we still somehow have to think in another way, perhaps. Okay. Now, again, the key point here is for this, where we are going with this, is that where the quantum potential is negligible, we have the classical world. And it comes out of the theory as relatively autonomous whenever the quantum potential can be neglected. And then we can treat this classical world as if it were independently existed. But again, to remember, actually, it's an abstraction from the subtle quantum world, which is being taken as the ultimate ground of existence in this model, in this ontology. So if you like here, John Searle, when he looked at these discussions of epistemological discussions and anti-realism, he asked, does the real world exist? And here we say, yes, it does, but fundamentally the real world is this elusive quantum world, but it does exist. This is the ontological interpretation, okay? And you see now, the thing here is, of course, that the classical world is extremely important. Why? Well, it makes possible objectivity and public third-person observation. And these are, of course, the things that philosophers love, logical positivists love this thing, everybody loves third-person science. Science loves the third-person perspective. Kind of, this is, for some people, this all we have to worry about, so we can ignore consciousness. But anyway, this is not my view. Still, so again, in the quantum world, there's no way to obtain an objective public display of results. Okay? Why? Well, because everything is so mobile, subtle, mutually interdependent. If you operate it in this quantum level, no way. But as I have said many times, in the classical subworld, we have events that are negligibly affected by our measurements and observations. And then, you remember we get particles, but also fields in the classical subworld. And that's what we use to convey information to our senses in a well-defined way. So, for example, light waves, for all practical purposes, we can think of them as classical. And the same thing with ink in our books and, stuff in the computers and all that. And we know of no other condition in which this could happen. Okay? So again, we could ask, so if we take things like perception and communication and ask, are they classical or quantum? Now, of course, we know that the eye can be sensitive to a few quanta at a time, but the reception of a small number of quanta gives only the vaguest sense of optical stimulation, Therefore, to have meaningful perception actually requires a large number of quanta, which is really a classical behavior. So we need the classical world to perceive anything. The same thing about communication, which Martti, of course, will tell us later on. Meaningful communication between people also requires classically describable processes involving a large number of quanta. So we really require the classical level. So a person who is interested in, if you like, quantum consciousness or quantum mind need not deny the importance of the classical level. That's one of the points, take-home messages. Now, so again, summarize, what is the importance of classical level? Well, the brain responds only to the states of particles and not to their wave functions. If you like, the brain typically responds to the more macroscopic stuff. Although there are some issues with that. And also, meaningful sense perception and communication has to go through the classical level, in which the effects of the wave function can be consistently left out of account. However, Now, of course, the question arises, so how do we then learn about the quantum world? And of course, then we make measurements. And through a process of amplification and recording in the stable structure of a measuring apparatus, the overall quantum world can manifest itself in the more limited classical subworld. So you see, a measurement apparatus has to have two parts. There has to be the classical, if you like, there's got to be the needle, which tells us what's the result. This is, of course, the key problem in quantum computation, because you've got to bring the quantum, whatever you do there, into the results have to be brought to the classical domain. And so, but then the measuring apparatus also has to have a quantum part so that it can talk to the quantum object or interact with it. And somewhere there has to be, it has to be able to amplify those results, and there has to be a recording device, like some irreversible mark, or preferably, okay? And so we have this picture of the that's how we get to know. I mean, otherwise we wouldn't know there is the quantum world. And of course, in some experiments, okay, black body radiation, photoelectric effect, those kinds of experiments, the quantum world began to reveal itself in the classical domain. And people were puzzled about these crazy results. They couldn't explain with classical physics. So if you like, the classical world, of course, gives us a hint that there is the quantum world. One thing, of course, if one would, the selling point of the theory that if you know that in, for example, in the von Neumann's version of quantum mechanics, you actually have to assume a cut between quantum world and classical world, and that's arbitrary. If you want, you can include the measuring apparatus, then you need another one and another one. Maybe consciousness collapses the wave function, okay? But in this case, you don't need the cut, and they will say that there is actually one overall quantum world which contains this approximately classical subworld that gradually emerges under certain conditions. And this is what Bowman Hiley would say, this has not been achieved by other interpretations without going beyond current quantum theory. So it's part of the game here. I think what Bohm felt very much he wanted to do with the book Undivided Universe. Let's see how far we can get with quantum theory without changing it. And of course, towards the end of the book, they also consider making, modifying it. But a lot of the book is just saying, what can we do with quantum theory as it is?
Can I just say that that was the second book we were going to write?
That's right.
But he
Yeah.
died, unfortunately.
Right. But anyway, but in some ways, I think Bohm also felt, well, what can we do with quantum theory? Let's see first what we can do with it, and then, Yeah. And this is, of course, that you can have this. Now, these are interesting questions, and of course, at somewhere here, I come to the limits of my, I'm a mere philosopher, so I'm sure people here understand these things much better than I do. But one interesting thing that I can get out of reading the Undivided Universe is that locality and separability are actually the result of non-locality. So they write that it's just the most characteristic quantum properties like non-locality and undivided wholeness that bring about the classical world, which is locality and separability into distinct components. So for example, if you look at the Bohm theory of measurement, what happens there is that it's the non-local quantum potential which is produced in the interaction with the apparatus and the object that will separate the wave function of the observed system into distinct channels that can be treated locally. And that's how we get our result of measurement. The particle goes into one of the channels, and then you get some kind of irreversible processes, so enough degrees of freedom. It's very unlikely that it would ever come back, and that's how you establish it. But the point here is, again, that it's this non-local quantum potential that in a way gives you these, if you like, classical possibilities. So in that sense, it's the non-locality that is prior to locality. And of course, you want to correct me.
No, I'd just say that it's the apparatus and the particle fuse into a whole. Right. And therefore they respond together to the common pool of information.
Right. But what is it that does creates the distinct channels in that process?
Because you separate the channels and make sure they are separated from each other. Right. In the weak measurements, you don't allow the channels to separate.
Okay.
Therefore, you're seeing something different going on. Okay. But the measurement allows them to separate. and then reversibility takes over. You've got to change everything to get reversible.
But the channels here are parts of the wave function, right?
Yeah, in this language, yes.
Yeah, yeah.
They're the wave packets, if you want.
Right, right. The options, like if you had two possibilities, you would have two channels.
Yes, and two wave packets, which are not overlapping.
Right, right, right.
Paavo, can I ask something about that? Is non-locality the same thing as do you use it in the same sense of like entanglement?
It's entanglement.
It's the same in the sense of entanglement. Okay, thanks. I mean non-locality in the sense of
Yeah, it's entangled. The wave functions become entangled.
Okay,
apparatus and particle.
Okay, I see. I will say something later.
Okay. And so now this is again an interesting, perhaps a philosophical point, perhaps even for the mathematicians and logicians, where if there's kind of self-reference, because we could say that what's happening here is that actually the overall quantum world measures and observes itself. So why? Well, the classical subworld that contains the apparatus it's really inseparably contained within this subtle quantum world, especially through those non-local interactions that bring about the classical behavior. Because it's somehow what makes this thing possible is really the underlying quantum world. So in that sense, the observing instrument is not separate from what is observed. But still, we have this relative autonomy of the classical level, and that's how the total quantum world can manifest and reveal itself within itself in a measurement. So without the classical world, there would be no measurements in this picture. And of course, we already said there would be no perception, there would be no communication as we know it. But then again, of course, it's not the... Of course, they say that in contrast to the classical notion of measurement, we should regard a quantum measurement as a manifesting process. Okay, now we go to consciousness. It's a little bit my own how much time do I have?
You have a little bit more.
Few more minutes.
Yeah.
I got my clock there, but okay. Anyway, I'll try to get to this part. So here you see, well, as we have maybe even said, implicitly here is that orthodox cognitive neuroscience typically assumes that the neural correlates of consciousness are processes which take place in the classical domain. And it's assumed that there's no need for subtle quantum effects when trying to understand how these processes function and why there is conscious experience associated with them. And now think about that in relation to what Bohm and Heiley are saying in the book. They're saying that the more fundamental ground of existence is the subtle quantum world exemplified by the properties of the quantum potential. And my question is, why should we assume that a holistic, subtle and subjective phenomenon such as conscious experience should be entirely reducible or explained in terms of the mechanical classical domain, which after all is an abstraction from the overall quantum world? So it's kind of a rhetorical question, but it's kind of intuition that's been driving me ever since I actually encountered these things. And this, for me, it goes back to the mid-80s when I was interacting with Bohm and then later on with Heiley. Anyway, so but this is kind of our dogma or the question that's keeping us here. And the way one question that I like to propose is very tentative and schematic, but I'm asking that when we are conscious, is the manifest classical world being presented as a subtle quantum world? Because you remember the hard problem of consciousness is the problem of explaining how and why physical processes give rise to consciousness. And I'm assuming that as long as we stay entirely within the classical domain, there is no consciousness. Nothing is conscious that is if it's only in the classical domain. If the quantum potential is completely connected. That's just an assumption that I'm making. And therefore I'm suggesting that consciousness often requires a certain kind of interplay of the classical and the quantum part of the brain. I'm also not assuming there's a quantum part of the brain. Of course, I'm saying often there because there could be cases like meditation or whatnot where we don't need the classical world. But in most situations, like what I'm perceiving now, the classical world is there. And so I would propose that conscious experience typically requires that aspects of the manifest classical world are being presented to the quantum part of the brain. And if you consider perception, so we are typically perceiving the classical world. First step is through the senses, which can be explained classically. Here again, I ignore quantum effects. People would call them trivial, like what's happening in the retina. I'll come back to that. But still, again, when sensory impulses are carried into the brain, many of these processes can be understood classically. So we can again grant that a lot of stuff going in the brain is in the classical domain, no problem. However, and of course, a lot of neuroscientists assume that everything interesting in the brain can be explained without quantum mechanics, okay? Now, this is of course a speculative assumption because we don't know, and we do have neuroscientists going back to Eccles and Beck. They suggested actually quantum processes may be important. We have now, of course, many others, Penrose, Hammerose, Staff, Freeman, and Whittier, and so on and so forth. And we do know that in the retina, already in the retinal cells respond to a few quanta at a time, and then there is a multiplication of their effects to a classical level in intensity. So we may not know it, but we are all walking quantum amplifiers. The thing that's happening in our retina. And then you could argue that retina is just an extension of the brain. Perhaps not everybody agrees, but we'd say that. And of course the argument goes, or question is, could there be other parts of the brain in which such a sensitivity may exist? For example, in certain kind of synapses or even in the microtubules. Okay. And so now we come to this point that if there would be this kind of sensitivity, then the brain would be like a measuring system that could, like a measuring apparatus, manifest and reveal aspects of the quantum world in the overall processes. And so in that sense, we could say that our perception and our action are actually analogous to quantum measurement. For example, then when I'm perceiving things, the process of perception would unfold into the brain, and then the speculation is that it would connect to this subtle quantum domain of the brain. And then this quantum domain may in turn reconnect to the classical domain, where outgoing action is determined through amplification of quantum effects. And this is actually a point that Bohm and Heilin make in The Undivided Universe, but they don't expand on it. And this is something that I like to take up and develop more. And I think we should look into it. And so now, of course, we could ask some questions. So what happens when the process of perception connects to the quantum world? Is information carried by the stable structures at the classical level being presented to the quantum world? And then does most of conscious experience arise somewhere in the process where the classical process connects to the quantum domain? Remember, I made the assumption that if you're staying entirely within the classical domain, there's not going to be consciousness there. So just, and of course this would lead us to a possible solution of the hard problem of consciousness. And so we could ask this question like, how does conscious experience arise? There is a suggestion of connected Bohm theory by Jack Sarfati. He has many wild ideas, but this is one of the, it's a wild, but it's not equally as wild as some of the others.
Using his name.
Yeah, I know. But anyway, he suggested that so-called back action would play a key role in how conscious experience arises in the context of the Bohm interpretation. And as you can see, we have above said it's the wave function influencing the particle, but if the field influences the particle, might not the particle influence or act back upon the field? This would be very much in line with principles of physics. And so actually this is something that Bohm himself considers already in 52 and Bohm and Heilin in 93. And so we could say that, we use the notion of informing there. Could there be a kind of equally subtle effect when it comes to the back action? And what Sarfati has proposed is that this qualia would be some kind of excitations in these macro quantum coherent pilot waves. The pilot wave is another term of this quantum field in the Bohm theory. And so the assumption there is that we got something intrinsically mental, namely this quantum information field, and then our qualia would be excitations in them, imprinted by the back reaction of the classical material vehicles. So again, we have the classical world exciting, if you like, this quantum domain. And anyway, so this does connect to the Furlick thing. I'll move on here. I don't say everything here. There is some controversy about these Furlick states, which are the macroscopic quantum coherent states in the brain. But there is some recent research suggesting that actually the group in Gothenburg claims to have observed for the first time a quantum coherent-like state. And there's some other connective work there. And of course, so it's just one idea. I mean, I don't, it's just to get started really here. But this would be one suggestion how classical processes become experienced. And of course, right now, when I'm observing the environment, I'm observing the macroscopic world, and somehow, if there would be some kind of back action making me conscious of it. But still some final point just is that, of course, we are typically conscious of an entire virtual world, perhaps produced by the brain analogously to the way holograms work. This is, of course, the pre-Brahm idea. So it could actually be that what is being presented to the quantum part of the brain is this 3D classical construct. And we don't know the mechanism, but anyway, this could come into it. So anyway, here's the summary of what I've been saying, and perhaps finally is just to come back that the suggestion that the brain would be analogous to this quantum measuring apparatus. But I think I won't go through all of that because of the time constraint. So thank you very much.
All right, thank you very much.
Could I make a comment?
Yes.
To begin with, as it's been plagiarising, advertising our work. Well done, Paavo. I think at long last I don't have to worry about you understanding what we were saying. You've got it very well, except for the last little bit of back reaction.
Right. What do you think about back reaction?
It's a different type of force, which is what I tried to say, but it probably got lost in my talk.
Right.
It's the force which is the force from within. It's the Coriolis force. It's the Magnus force which keeps aeroplanes flying. There's no back reaction in that. So there's a different quality of force.
But we could have another way in which if you like, the quantum level would be sensitive to the macroscopic world. Of course, we do have that through the boundary conditions. Like even in the two-slit experiment, it's the classical environment that will.
But it's through the quantum potential that's doing this. This is why I wanted to, in my talk, to justify the quantum potential was not our invention. It's an essential feature of all of physics.
But it responds to the classical environment, right?
Well, I don't look at it as classical.
Yeah, I think the idea is maybe that there is this one environment.
Yeah.
Collectively.
You see, because can I just have a few minutes? I thought very much that we could think of this. We don't need decoherence. At least I've got one example which doesn't need decoherence, and so that's what worries me. And I don't know quite what to do with it. But I was watching Formula One racing, and there we have the Kerr's process, which is very interesting, where you store you brake, you store the energy in the battery, and then when you accelerate again, not only do you use the petrol, you also use the quantum potential is very much like a store of energy, which you take from the classical quantum kinetic theory. And put it in a store somehow. And this is the idea of the non-local energy. It's not pinpointed. And then when it comes, and during the interference effects, it's that extra energy is, as it were, guiding in the language that Paavo was using, the particle, and that's what makes those trajectories look like that. Now, I thought, well, okay, what happens if I put my quantum particle on top of a upside down? I think about the inflation, which I know Roger doesn't like, but it's a lovely potential, okay, which you don't, normally we have it this way, let's have it that way. And you've got a Gaussian wave packet on the top there, and then you let it fall. It accelerates, and if you work out the trajectories, they actually become classical. So you can actually go from the quantum trajectory into the classical, no decoherence, but it could be somehow due to this mass effect. You're increasing the mass of the particle. In this case, you're increasing the speed of the particle, but Roger wants to say you increase the mass of the particle. So that's another possibility. How we do it experimentally, I don't know. But you see, there's no decoherence in that at all.
No decoherence.
No. So don't
yeah,
always
but-
go
But
for
so
it.
you
The
can't-
decoherence is important, please don't get me wrong.
No, I understand the point.
I think Demi's had a question as well.
Yeah, quick question. Thanks for coming over. It's great talk.
Yeah.
So this irreversibility that you talk about with the quantum anti-classical, just struck me as having the right kind of properties to explain direction of time. Is there a sort of relationship between them?
I think people have sometimes used that as one of the something what happened. I mean, some people would say it's a collapse of wave function. You might also do it that way, but that would be a bit like a thermodynamic.
Then you have to go to thermal quantum field theory to really appreciate where that's coming from.
Yeah.
That's another lecture.
But it's definitely, you can definitely access it in this kind of a model.
Yes.
You can also then access it in the kind of models that I propose. But you can make modelizations where there is directionality and modelizations where there's reversibility and no.
Well, it seems like there's, yes, it's been built in, right, the directionality.
Yeah.
But in a way to perhaps still say something about the motivation of my talk is that in the bone theory as it is, we talk a lot about how the quantum potential organizes physical process. But in some sense here, like with consciousness, we're interested, well, how does the physical world and the manifest classical world get experienced by us in consciousness? And if we do believe that the quantum potential is involved in those processes, then the idea of some kind of back action, it could be something else. I mean, I don't have strong opinions about
I think
it.
there is.
But there's something like,
be something, but we
that's
don't.
right. The Bohm would call it soma.
Tell us what it is.
Bohm would call it soma significance, or some kind of where somehow, if you like, the magic of perception is that we are able to become conscious of, like in this case, of the environment. And if we seek like a physical explanation of that through quantum mechanics, then we would need not only from quantum potential to manifest particles, but also from the manifest world back to the quantum world, if you like.
I have one question.
Right.
Is it okay? Anybody else?
Well, I just want to don't forget when you go to field theory, you get the superquantum potential.
Right.
You get a whole hierarchy.
Yeah, that's right. Joseph, you had a question?
So to Paavo,
Yeah.
what's the difference for you between consciousness and perception? Why isn't all consciousness at the end perception?
Well, of course, we can be conscious of our thoughts. I mean, usually we say perception and cognition, so we might have non-perceptual conscious events. So consciousness would be the broader category.
I mean, we usually say, philosophers say, there's a difference between perception and intellection or conception.
Right.
But why isn't consciousness, and so I'm aware of the distinction, but why isn't it that there's perception, and sometimes I perceive you, a classical world, and sometimes I perceive myself, not just my me, but as it were, things inside of me.
No, I would.
Because a lot of what you say is leading there.
Yes, I would, because I have to qualify, of course, that there are cases of conscious experience where we don't need the classical world, it's the internal aspect. But of course, typically when we are perceiving, then typically what we do perceive is the manifest world, and we do not perceive the quantum world directly. So, but you see that?
I'm going to ask for the impossible. I'm going to ask a really tricky question, and I'm going to ask you to answer in 2 seconds, so that we can move on to Stuart. But it's sort of also a proposal for everyone here. I think, there's sort of a model of consciousness proposed by Chalmers there on the board. And Paavo, you're talking in this way where you say, hey, I'm going to take my ontology to be sort of this Bohmian quantum world. As far as I understand the Bohmian quantum world, there still are, let's call them like non-temporal processes happening in it, in a way that needs talking about. There are different proposals for it.
Time might not be defined, you see, because
I know, exactly. So here we are. So in a way we have sort of you're leaning on kind of an ontology that itself still is unresolved. Rogers made proposals about how to extend it. In a way, actually, the whole Bohmian interpretation is a proposal of that. But I want to make things hotter still. So in a way, we also need to be able to, in our thinking about consciousness, sort of if we think about the I poke at something, it reacts and it does something sense. Well, there's things like, Hugh here. Gosh, you poke at Hugh and, he comes up with the, solution to CH. It's unclear to me that that conception that Hugh is holding can actually be meaningfully discussed as some kind of a submodelization, let's say in a Bohmian or even the extended Penrosian kind of conception of the world you've made. So I would just say in a way that big part of what I was saying yesterday has to do with these types of challenges. So it's of course conceivable that Hugh is just really carrying out these physical processes and he's sort of pitching us something very fancy, but it isn't really there. But that seems unlikely, just the same way as it seems unlikely that the LIGO experiments are figments of our imagination. Right. So one thing is a proposal to all of us, and then in this world that you talk of now, how do you see, so to connect to Julia, this is a question for both of you, is that, so actually, I think maybe Julia might think that maybe you could have classical system where there's consciousness connected to a quantum world, but how do you see the connectivity between, so can the Tononi IIP model live in a sort of a Bohmian universe? Does that make, does the question make sense?
Well, I could say just that, of course here I perhaps didn't make it clear enough, but in some ways I think the aim of Bohm when he worked this thing out was to, at least the early part was to see how far can you get with quantum theory. Yeah. And Bohm would have been the first to emphasize that quantum theory is still limited. It won't be, so it probably wouldn't be able to discuss the kind of things that, but of course, Bohm also had a more general philosophical ambitions, and that's where the implicate order framework comes out. And in there, I presume there would be room for the mathematics or perhaps IIT in a different way. But this is more just like looking at what is quantum theory if we don't change it. What is it trying to tell us? Yeah. And there are going to be limits. And of course, we're stretching it if we're trying to say, could we use that to say something even about consciousness? Yeah. And take the David Chalmers in double aspect theory of information and like that. But I don't know if Giulio has something.
Yes.
Yeah. So there can be classical consciousness, right? You can live in a Bohmian universe.
Yes.
Yes.
The
Okay.
yes to that.
Thank you very much. Okay. Thank you guys.